Hi, I'm Wenqi. I'm going to present our paper, S-cube nerve, Neuroreflectance field from shading and shadow on the single viewpoint. This is a joint work with Guanyin, Chaofeng, Zhenfang, and Canis. 3D reconstruction from images is a central and important problem in computer vision. Multiple stereo methods, which capture a target scene from multiple viewpoints under a fixed lighting condition, are widely used for scene reconstruction. However, they often assume surfaces with Lambertian reflectance and have difficulties in recovering high-frequency surface details. An alternative approach is to utilize images captured from a fixed viewpoint but under different point light sources, which is adopted by photometric stereo methods where shading information is utilized to reconstruct surface details of non-Lambertian objects. However, these single-view methods only consider the visible regions and ignore the invisible shapes in the scene, for example, the cube behind the ball. Given a monocular scene, they mainly represent the scene structure as normal or depths. However, it's non-trivial to obtain accurate depths from normal integration. And depth map cannot describe the invisible regions. Compared to these structures, the neural field adopted by our method is capable of modeling the complete scene geometry. Specifically, we exploit both the shading and shadow cues in the monocular scene to reconstruct both visible and invisible regions. Given three different objects, which have the same front view but with different shapes in the back, we can see that although these objects have the same shapes and appearance in the front view, the produced shadows are largely different, which demonstrates that shadow can provide strong information for shape reconstruction. In this work, we propose S-cube nerve to jointly optimize shading and shadow using Neuroreflectance field representation. For each camera ray, we first apply root finding to locate the surface point. MV points on the camera ray are sampled around the surface to generate accumulated shading values, and L points are sampled on the surface to light segment to calculate light visibility. They are multiplied to output the final RGB value. Since there's no multi-view information to constrain non-sample regions, we double joint volume and surface rendering strategy instead of gradually shortening the sample range to refine the surface region. The light visibility is calculated by accumulating occupancies along the surface to light segment. We calculate the light visibility for the expected surface points in an online manner. Other alternative shadow modeling methods either calculate light visibilities for all points sampled along the camera ray, which is computationally expensive, or adopt an MLP to directly regress light visibility of a point to speed up shadow computation. Here we show some experimental results. We first show the scene relighting results under a fixed viewpoint. We can see that both the predicted shading and shadow are consistent with ground truth, which demonstrates the effectiveness of methods in scene reconstruction and decomposition. We also show the rendering results on the novel views. We can see that our method can properly reconstruct shapes of both the visible and invisible regions. We also analyze the effect of joint shading and shadow modeling. We can see that without shading information, the model totally fails to reconstruct scene, and without shadow information, the model fails to predict the depth and shape of the object since there's no constraint on invisible regions, while our method properly reconstructs the full scene with both shading and shadow cues. For more results on our paper and code, please visit our project page. Thanks.